Got it. Okay. Yeah. Thanks. Okay. Okay. So, ladies and gentlemen, sorry for the delay here. It still looks like we're oddly low in terms of numbers today, but I'll want to get going here. So, today's discussion is going to take us through two major and very different topics. On the one hand, we're going to be discussing the use of models which incorporate geographic information and incorporate information related to agent movement within that geography. Secondly, in preceding that, we're actually going to be examining the use of several different types of models, namely system dynamics and agent-based models, to look at equilibria behavior with respect to these. Both, and to look specifically at solutions to equilibria in the context of differential equation models. This is a type of exercise we've worked through before. It's a type of exercise I wanted to get you comfortable with because it is important to the course. So I had provided for you on the Moodle site a document which you could examine, which provides examples of solutions to two major sort of system dynamics models. On the one hand, one with an open population where we have a inflow from an external source, in that case immigration, and we're solving for the equilibria associated with infection spread. Secondly, I examined the case which I had asked you to examine for in the context of your work, which was focused on a situation where we have turnover within a population, not in terms of the population itself, but in terms of people recovering from infection. So within this document I've provided on Moodle, you'll find the first case, equilibria for an open population, and secondly, further down, equilibria for a closed population with loss of immunity. This is the case that I asked you to solve because it corresponds to an any logic model that we're going to be working with and that I'm going to provide for you also through the Moodle site, or which is provided right now. Okay, so I'd like to go over that derivation just so that you're familiar with its broad outlines and so that we could examine some of its interpretation. Okay, so the model that we're dealing with is shown here in differential equation form. I'll show you the corresponding model here in just a moment with any logic coming up, the corresponding any logic model. But probably someone here should be able to interpret for me basically what this model involves. So using those equations, can anyone read off to me what's going on within this first equation? This equation involving the rate of change of S. What are we seeing here in terms of the inflows and outflows to this model? Can anyone tell me? So when we see this equation here, what's the inflow? What does that represent conceptually? Yeah, it's loss of immunity. It's people who were in the R stock, the recovered stock, and are losing immunity with a certain chance per unit time given by omega, a certain hazard rate. So the average amount of time within the R stock would be what? If this is the hazard rate of them going from the R stock, oops, this guy here, to susceptible, what is the average amount of time they spend in the R stock? 1 over omega, yeah. Okay, what does this term represent? Yeah, this is infection here. So people have C contacts per unit time overall. This is the fraction of those that are posited to be with infectious people. So if they have 100 contacts overall per day, and half the population is infected, I over n is 0.5. Then they have 50 contacts with somebody per day, infectious people on average per day. The C is contacts with anyone. C times I over n is contacts per day with infectious people. Each contact, they have a chance probability beta of getting infected, and so we approximated the entire chance of being infected as C times I over n times beta. That being called, what do we term this C times I over n times beta? What do we term that? We have a special name for it. Force of infection. That's the chance per unit time, the hazard rate by which susceptibles are infected. And we multiply it by susceptibles to get the number of susceptibles who are infected per unit time. Okay, so the force of infection is in units 1 over time, and we multiply it times people to get people per unit time. And this is the inflow from that. So these are the people getting infected, therefore flowing out of susceptibles, getting infected, flowing into infectives. This minus I over tau is consists of a term for allowing recovery from infection with an average time infected of what? What's their average time infected here? Tau. Good. And this is the inflow for that to recovered stock. Now, because this population is circulating among S, I, and R, it's not leaving. It's not new people aren't coming in. New people aren't dying. The total population is constant. S plus I plus R equals N, and therefore we can express N as some fixed number minus S plus I. So we don't need to solve for I. We can just solve for R. We could just solve for S and I, and whatever the values of S and I are, we can determine R through this equation here. It's N minus quantity S plus I. Okay, so we can in short go to something like this. Now, I say here that we want these things equal to 0. Why do we want those equal to 0? I want to make sure everyone has comfort with this. Why do we want these equal to 0? Why are we solving for S dot I dot equals 0? Yeah, at equilibrium, things aren't changing. The stocks aren't going up. They're not going down. So at equilibrium, if S is in balance, the inflow equals the outflow, right? And S dot is 0. Inflow equals outflow. The stock is not rising. It's not falling. It's staying in equilibrium. And similarly, we want I dot, the rate of change of I, to be 0 as well. So the inflow equals the outflow. So that equals 0. And if we have those being 0, given that that's a fixed population, R dot is 0. Okay. Now, we can then factor this. If I dot is equal to 0, recognizing here that we have an I in both these terms, we can pull that out front. Here we have I times C times beta times 1 over n minus 1 over tau equals 0. And simplifying here, we get something like this. Does anyone recognize what's the C times beta times tau? Anyone recognize that term? That's a term of significance. It's actually a very significant term. It means something. C times beta times tau. What is that? Anyone recognize it? Yes, it's R0. R naught. It's the number of people infected by an infective over the course of their illness before they recover, if they're surrounded by what? Totally susceptible other people. That's right. So C times beta times tau is R0. How do we know that? Well, look, each of those infectives comes into contact with C people per unit time. By definition, with R0, we're positing all of them are susceptible. So for each of those people, we have a chance beta of infecting that person. So maybe we come into contact with 100 people per day total. Beta is 0.1. So on average, we'll infect 10 people a day, 100 times 0.1. And then what's tau here? Mean duration of infectiousness. So why am I multiplying by that? Because for each of those units of time, say 10 days, suppose it's 10, each of those 10 days, I'm infecting 10 people. 100 people per day, all of them susceptible. Each of them have a chance of 0.1 to be infected. So on average, it's 100 people, 100 people per day I meet. I infect 10 of them per day times 10 days that I have the illness, say. That's 100 people over the course of my illness. Does that make sense? For something like measles, it's something like it's like 16. So you infect 16 people if you're surrounded by people, measles. So that's actually R0 there. And that's going to be important in the solution, it turns out, to interpret it that way. Okay, so ladies and gentlemen, there's really two possibilities here for an equilibrium, okay? One is where, well, what's one obvious one? What's one obvious condition under which this thing will be zero, if what equals zero? Yeah, effectives equals zero. Look, if effectives equal to zero, this thing is going to be equal to zero. And then we can go solve for other things too. So we know half of it effectives equal to zero. Doesn't matter what this thing is now. And having effectives equal to zero, then we can plug in that into this guy here for S dot. Plug in effectives equal to zero. This term entirely goes away, the second term here. And then we have omega times n minus s equals zero, which applies n minus s equals zero, which applies what? If n minus s equals zero, what is the case? Everyone's susceptible. So if nobody's infective, everyone's susceptible. Good, thanks. Everyone's susceptible. So that's the disease-free equilibria case. Now, what's the other possibility? What's the other possibility by which this will be zero? So again, we said, look, we want S dot and I dot to be zero. And we started solving this one just because it was a bit easier. We could factor I out of it. So we dealt with this case for I. What's the other possibility by which this could equal zero? If what equals zero? Mumble. Well, we'll get to that about how many people are recovered. But what's the other case by which this term, just speaking mathematically, either I equals zero or what else equals zero? This whole thing equals zero, right? By the way, what's that going to tell us? What do you think? Under what conditions for S would this thing equal zero? If S equals what? N over R0. And it turns out that's super important because it's telling us basically an equilibrium, in a dynamic, sort of an equilibrium where it's still circulating. Some people are infective. The fraction of the population that remains susceptible is what? 1 over R0. Why does that fraction remain susceptible? Well, we'll come to that, but think about it. Think about it, because you'll have to remember what's the other criteria for equilibrium. We'll come to why that has to be, that S at equilibrium, S equals 1 over R0. Okay, let's go down to that case. So we did this case here, where I equals 0. Now let's go down to this case. This is a bit gnarlier, okay? S is equal to this. We solved that already. Okay, now, this tells us sort of at equilibrium, this must be the case. Now we have to solve for I. And we've already dealt with the equation for I dot. That's how we got this whole thing. So the only other piece of information we have here is S dot, or the other relevant piece of information. So we're going to need to solve S dot, given that we know that S is N over C times beta times tau, or R0. Okay, so we're going to have to solve this guy, given that we know what S is. And this gets a bit gnarly, but let's go do it. So S dot equals that, which implies all this. And then we're going to substitute in here the value for S that we derived here. This guy here gets substituted in. We got rid of that S, and it got substituted in over here as well, because there's two S's here, right? Going and simplifying, we can go and make this all a little bit simpler through some manipulations here. Amongst other things, we can multiply through. And here we are going down, and this is what we're actually this is what we actually derive here. How did we get from this guy down to this guy? Can anyone tell me? What did we do here? Yeah, it's actually a sort of involved process, but basically we're canceling this n with this n here, right? This c cancels that one, this beta cancels that one, and so all that's left is I over tau. That's how we simplified, right? And this guy here is just duplicated as such. So that allows us to go and further sort of work this thing through. Here we're grouping the terms involving I because we need to solve for I. Everything else here is a constant. N is a constant, C is a constant, beta is a constant, tau is a constant, omega is a constant. So we just have to group the things involving I. So we kind of go and we group these guys together, and then we get a bunch of constants over here. We move them. We move this guy to the other side because it's got some negatives. We want to turn it to positives. We could divide through here by I, and basically what it comes down to is it looks like this. Okay. Now we're going to talk about the interpretation of that in just a second, but it turns out that each of these terms is significant. This n times c over beta times tau is n over r0. It's the fraction that are susceptible. And it turns out omega n times tau is a dimensionless quantity. So having to do with sort of the rate of losing immunity compared to the rate of recovering. If the rate of recovering is, the rate of losing immunity is higher, or the rate of recovering is lower, or sorry, the time spent infected is lower, as long as their product is the same, we're going to have this term be equal and this term be equal here. So we can do some work just by solving for n minus I minus s at equilibrium, and we get this. So the endemic equilibrium here, where there's some people infected, that's what we mean by endemic. Some people are infective is s is n over r naught. I is this whole term here, and R, ladies and gentlemen, is this term here. Okay, so we just solve for that. So you may ask, well, what are those terms? What are their interpretations? And I comment on here, or what these on the interpretation here. Okay, so first of all, sort of these things are based on natural sort of quantities, not individually on C and beta and tau, but really on natural combinations of them. So omega times tau, what are the units of omega times tau? Can anyone tell me? This will be important for a later lecture. What is omega, the units of omega? That's my hazard rate. That's my chance per unit time of losing immunity. What are the units of that? 1 over time. What are the units of tau? Time. So when you multiply them, it's dimensionless, meaning it's independent of unit system. It doesn't depend on the units we use. It's a quantity which is independent how we measure time. Okay. Similarly, C times beta times tau. What are the units of that? I'll give you a hint. C is 1 over time. Beta, what are its units? It's dimensionless. It's the fraction of times we get infected. It's like number of coin flips that turn out heads. It's coin flips in numerator, coin flips in denominator. So it's unitless. It's dimensionless. It's of unit dimension. We can measure coin flips in tens of coin flips, thousands of coin flips. The numerator and denominator are measured the same way. They cancel. Tau, what is that measured in? What is that? We said it earlier. It's time. So C times beta times tau is also dimensionless quantity, meaning it's of unit dimension. And it turns out that's the way the world has to be able to be described in unitless terms, because it doesn't care about our unit systems. So n over C times n times beta, That's a certain fraction of this. It's n over r0. It's a fraction of the population. And c times beta times tau is r0, and omega times tau is another quantity, okay? So it's these products that are important, these dimensionless products. The fraction of the population that remains susceptible in endemic equilibrium is 1 over r0. Why is that? Why is it that the fraction of the population that remains susceptible at equilibrium, for an endemic equilibrium where there are infectives, why does it have to be the case here that the fraction of the population that's susceptible is 1 over r0? Why is that? Think about that. Why is that? Under what conditions will the system being in equilibrium? Remember we talked about it earlier. Under what conditions say, well, the number of infectives needs to be going up or down? We talked about it earlier from an aggregate perspective. Under what situation would the number of infectives be going either up or down? Talk about it in terms of flows. If the infig goes outflow, good enough. So that's one criteria. But the other criteria that I gave you, which I want you to remember, it was defined at an individual level concerning a particular infective. And I argued that the number of people going in the population who are infected will be going up if they do what? If for more than one person by the time they recover, right? They will have left the world a worse place than when they came into it. If they infect more than one person by the time they recover, they started just one person infected, and when they recovered, there's more than one person infected. And so they've left the world a worse place. There's more people infected now. So as long as an infective can infect more than one person over the course of their illness, as long as they can infect more than one person over the course of their illness, the number of infectives will be going up. If they infect fewer than one person over the course of the illness, the number of infectives will be going what? Down. So in what case will it be in balance? If they infect how many people over the course of their illness? One. They just replace themselves, right? Huh? They just replace themselves over the course of their illness. Under that condition, it will be in balance. And ladies and gentlemen, if they infect, if they're surrounded by all susceptibles, they infect how many people? By definition, by definition, they infect how many people over the entire course of their illness if they're surrounded by all susceptibles? We have a special symbol for it. R naught, R0. This is R0. This is the number of people they infect over the entire course of their illness, right? If they're surrounded by all susceptibles. So if they're surrounded by only a fraction of susceptibles, 1 over R0, how many people are they going to infect? Only 1 over R0 if the people around them are susceptible, not all. Suppose there's alpha percent. Suppose the fraction of people around them are half. Suppose the fraction of people around them that are susceptible are 1. Everyone around them is susceptible. They infect how many people? I'm just repeating what I said earlier. How many people they infect if alpha equals 1? In other words, if everyone around them, oh my gosh, is susceptible, how many people they infect? R0. Suppose half the people are around them are susceptible. How many people they infect? R0 over 2. Suppose a quarter of the people around them, 1/4 of the people around them are susceptible. How many people they infect on average over the entire course of their illness? R0 over 4, right? So suppose 1 over R0 if the people around them are susceptible. How many people do they infect on average? 1. R0 over R0, right? In other words, they're replacing themselves with exactly one person. In other words, the number of infected people is going neither up nor down. They've exactly replaced themselves. It's in balance, ladies and gentlemen. So it's got to be the case that the number of people around them, the fraction of people around them that remain susceptible is 1 over c times beta times tau in equilibrium. It's got to be the case, because otherwise it wouldn't be in equilibrium. If it were greater than this, it would be going up. If it were less than that, it would be going down. So, ladies and gentlemen, this fraction of people that remain susceptible in equilibrium is extremely important. It throttles the other components of this. Okay, it throttles them in terms of the sort of the number of people, the efficiency with which infection can spread. Okay, and basically here we have some additional terms related to essentially competing factors. The quicker they lose immunity, and the longer that they stay infective, sort of balance each other. If you have people who stay infective for longer, and you have a sort of less chance of losing immunity, if omega is smaller, they kind of balance, they counteract each other. In terms of this term, you can either have high one, low in the other, or low one, high in the other, etc. And then this is R0 here. Okay. So this has some interpretation to it in terms of fractions of the population. And you'll notice here, omega is just equal to what times, I is equal to omega tau times what? What other thing looks just like this? Here. Yeah, R. So the bigger omega tau is, the bigger this factor is. So if we have a higher rate of losing immunity, we lose immunity quicker, or we have a higher amount of time we spend infectious, it'll tend to increase I compared to R. By contrast, if we lose immunity more slowly, we stay in R for longer, right? Or if tau is shorter, in other words, we recover from infection sooner, it will also tend to raise R. So the bigger these things are, the faster we lose immunity, the longer we stay infected, the bigger I will be, and the ratio of them will be omega times tau, basically, the ratio between these, I over R. So that's an interpretation here. This is an equilibrium, and it comes out of the system dynamics model in terms of the equations that we have. Okay. Ladies and gentlemen, we have a system here which we could solve in terms of its equilibrium, and I'd like now to go instead to look at the actual system itself, which is going to be further characterized by an agent-based model. Okay, so I am going to here go and I'm just looking. You can go download it from the website. It's a thing called SIR model ABM and SD. ABM and SD for alternative networks extended take-home exercise 4 solution. Okay, and I will go. I thought I put it on my drive here, but I'm having trouble finding it. So this is the model that I asked you to experiment with a little bit by running different scenarios with it. Okay. So here we go. It may be that it's treating it as read-only or something silly like that. So we'll try this again. Okay, because I'm using this lab computer, I'm having a bit of a difficulty. So let me go to Moodle and just do that. Okay, let me get to Chrome, Moodle, yes, okay, and here we go, log in. Boom. Okay, so I had asked you to explore this given system using both a system dynamics model and an agent-based model. And as part of that, we had previously looked at some of the implications for behavior over time. This time I asked you to take a look at the impact both in terms of a state space plot on the one hand and in terms of behavior over time on the other, between these two models, between a system dynamics model and a model that was an agent-based sort of analog to that. So can anyone talk to me, how did, exception. Ladies and gentlemen, this is how not to write software. Exception. Okay, so let's try that again. So I'm going to try, okay, so it knows about me now. Happy. So let's go down and download this model. Here we go. Okay, so opening this model in any logic here, we're going to see a system dynamics version and we're going to see an agent-based version, right? So here we go, and we're opening it up. So what were some of the differences between these two versions of the model? So we have a system dynamics, susceptible, infective, recovered. The number of immigrants per month is set to 0 by default. So basically, it's the system we've been talking about using the derivation that we've worked with. Okay. So can anyone tell me, within this system, we come to an equilibrium, but we also have an agent-based model characterized by individuals susceptible, infective, recovered, a corresponding system, just as individuals can go from susceptible to infective with a flow, infective to recovered with a flow, and then flow back to susceptible. We have an isomorphic series of transitions here. The details of how they're mediated is different because we have messages here and a certain probability of getting infected. And I asked you to look at this in the context of some graphs which I created. These included some graphs we already had from earlier work, but it further included a state space diagram here. And although I wasn't explicit about it, and this was my fault, I also was interested in examining it for different networks. Here we have a scale-free network, ladies and gentlemen, associated with this. For your cases, you might have examined other networks, and I'll give full credit for that. What are some of the differences you saw between the agent-based and system dynamics model? Can anyone say? Did both go to exactly the same equilibria? Did the system dynamics model go to an equilibrium? Did it go to a situation where the stocks were in balance? Anyone? Yes. Okay. Okay. I wholeheartedly agree that it went to an equilibrium. You could see it right here. So the number of susceptibles drops. It rebounds. Why does it rebound? Why does it rebound here? Yeah, inflow is greater than outflow. And why is if inflow is greater than the outflow for susceptibles, what does that mean? What is greater than what? We go look at the diagram here. If inflow is greater than outflow for susceptibles, what does that mean? That what is greater than what? Yeah, this waning of immunity, people going back here to susceptible is greater than what? Incidence, right? The rate of people getting infected. And so susceptibles comes up and it declines again. And there's behaviors associated with this that drive the number of infectives. The number of infectives goes towards an equilibrium in a damped way. It oscillates, but is damped out. And then so does infectives, and so does recovereds. Recovereds being the other part of the population. Viewed in a state-space way, ladies and gentlemen, we also get a sort of equilibria behavior shown. That's shown here in SD, this guy here. We can see it sort of goes up. So here, what does it mean if this line is going kind of in this direction with a 45 degree? What is that telling us? What does it mean if it's going like this in state space? Remember, it's number of susceptibles on the x-axis, number of infectives here. So what is this doing? Yeah, susceptibles are turning into infective, more or less in a one-to-one process. That's why it's at 45 degrees. when it goes off of 45 degrees, like it's no longer 45 degrees here, what's going on? Why aren't susceptibles and infectives just being traded off on a one-to-one basis? Because infectives are now starting to what? Recover, yeah. And then we're going down here. What's going on in this point? Why is it going down like this? Because the number of what are going down? Infectives. So number of infectives went up, right? That's the red curve here. That's what you could see here. And then it turned around. Number of infectives goes down. Number of susceptibles is initially not going down. It's not really decreasing here. And then it starts to rise because people start coming in. It's going down only a tiny bit. And then it starts to rise because people are coming in from recovered waning immunity. And it sort of cycles to this equilibrium. Okay, now, how does this compare, ladies and gentlemen, to what you get through agent-based runs? Here's an agent-based characterization. Here you could see in blue the agent-based characterization. Does it go to the same equilibrium always? No. Why not? What's different? Give me one major thing that's different between the two. Stochastics, ladies and gentlemen. Stochastics. And in the agent-based model, an individual has a certain probability of being infected. They're either infected or they're not. In the system dynamics model, we have sort of fractional people being infected. So that's good, but there's something more than that. Why is it that the infection goes completely extinct? Can anyone tell me? Why is it going extinct entirely? But in the ABM, but not the... Okay, this one actually didn't go extinct. This is with scale-free network, as I've asked you to download. You may have been running it with a different network, which again is fine. You'll see difference between the networks. Here, once again, scale-free network. Notice this is the number of people infective in the ABM with the SD. You could see the stochastics here, up, down, up, down, up, down. What? This is a reflection of the fact that sometimes more people get infected, sometimes less. And it has kind of a cyclic quality to it. Because after all, there are oscillations associated with stocks and flows. If the number of susceptibles gets too high, there'll be a bit of an outbreak, even if it's through chance. And if the number of infectives gets too high, it drains susceptibles and it'll drag infectives down again. So here you could see really the aspects of stochastics that were emphasized. Remind me your name? Bryce, as Bryce emphasized. Thank you. So there's another aspect, though, too. Like here, I didn't see an outbreak at all. There was no outbreak at all. Here, we're going to have an outbreak. So that's another stochastic component. But then you see a further issue. What happened here? What happened to the number of infectives after this point? Was it just not tracked? What was going on after this point? Well, we could right-click on this, say copy all. We could go over to Excel, for example, and we could dump this into Excel. And what we will see at the end for infective ABMs, notice these are all integers, something we'll get to in a moment. At the end, what will it be? Oh, gosh, it only does 1,000. It only shows 1,000. Bummer. Okay, what is it here? What's going on here? It's 0. Okay, let's try that again. We'll run it again, okay? Another time. Goes to 0. What's going on? Why is the ABM going to 0 sometimes? Why isn't it popping back from 0? You notice when it goes to 0, it typically stays at 0. Why? Here it's staying at 0 all of the time, it looks like. Well, after the initial one. Here it goes to 0 early on. Why is it not pouncing back after it goes to 0? There's no one infective. So there's nobody infective. No one's going to get infected. Right? So this is quantized. It is stochastic, but it's also quantized, meaning you have 0 or 1 or 2 or 3 people. In a system dynamics model, you can have as few people as you want. You can have 0.001. 0.002 people, 10 to the minus 9 people can be infective, and they'll still infect others, right? It will build up. It's just very small rate of infection will occur, but it's not truly extinct. It goes towards zero, but it's not actually zero. Whereas in an agent-based model, it's actually quantized. It's actually, you know, a difference in the sense that you have 0 or 1 or 2. And once it's 0, it's not bouncing back, right? It goes extinct. You could see it's not a bad approximation as long as it's continuing. The agent-based model kind of oscillates around this point, but then it goes extinct at the end. Here it is in state space, right? It sort of loops around it, but you could see there's a little bit of a difference in the number of susceptibles here between what the ABM projects and what this projects. This is kind of the equilibrium here. And if you put aside stochastics, the equilibrium for the ABM is actually shifted from that. It's roughly the same number of infectives, but it's shifted over the number of susceptibles, okay? So here are, some differences between them. Now, these runs, as I indicated, and as I welcome on the assignment or the take-home exercise, these runs are contingent on network. So some of you may have used, for example, a random network here, okay? Same average number of connections, about 10. Here we go. Here's a random network. This is the same model for which we previously derived the equilibrium. And here you can see a bit of approximation with the ABM in terms of its overall initial flow, but then it does go extinct entirely, partly due to stochastics. Here's a case where it doesn't go extinct, and you can see it's actually closer to the equilibria predicted by the system dynamics model in which we solved for, okay, where the fraction susceptible is the whole population divided by R0, by R0, okay? And you can see still stochastics there. We'll run it again. And what we'll see is pronounced differences between different runs, right? Sometimes it goes like that, and sometimes it dies out, and sometimes it doesn't. So here with a random network, it has a bit better chance of staying resident than some of the other network types, okay? Here, though, it did end up going extinct. Just by chance, by luck of the draw, it went extinct. There were 0 people who were infected at any one time. Maybe some people got recovered early and just not enough people got infected recently, and so it went extinct. Okay, if you tried a different network type, so that's a random one, and that's where it's closest to the system dynamics model. If we tried a different one, let's go try one that's, say, a distance-based. Is this very similar or very dissimilar from a system dynamics one? Turns out it's quite dissimilar. It dies out very quickly. Why does it die out? Why does it tend to die out if it spreads? This one is spread in a local fashion. Why does that tend to die out? Anyone? Whereas, say, a random one is more likely to survive, or a scale-free one is more likely to survive. Why is this sort of localized transmission more likely to die out? You can actually see the patterns if you run it slow enough. I'll try that again. Why is it that this one is more likely to die out? Here it spreads. Yeah, it's spreading through neighbors. Where are people recovering fastest? So if we consider of those who have been infected, where are the ones that are recovering? The ones that what? Yeah, the ones behind, the ones that are furthest back in time. And often those are separated from the wavefront of infection. It's like a prairie fire, right? It spreads out, and by the time there's new flammable elements back in the middle, the edge of the fire is far away. And so there's a lot less chance that it will spread to that new generation. It's not impossible. You notice there's some folks pretty close by. There's a little bit of reinfection there. This one's proving a little bit more persistent than on average. There's a little bit of reinfection, but chances are it will die out pretty darn soon, ladies and gentlemen. Pretty darn soon. So when you have these sort of localized transmission, there's a lot less chance it's going to persist. That's not really captured Well, by the system dynamics model in any way. And hard to kind of imagine quite how to capture that. You could do it in sort of a crude way by having stocks for different regions or something. But this is a significant issue. It's a significant issue that we might want to capture. And really, by going to a spatially explicit model, we can do so much more effectively than with an aggregate model. So here, with a very localized model, there's a big difference. The difference in stochastics and quantization really come out. The fact that there can't be 0.0001 people infected, still infected, waiting for, when the first susceptible comes back to a region. It doesn't work that way. Once it goes from 1 down to 0, that's it for that region. Okay? So here we have a trajectory here in state space that's rather different from what we see from the graph of state space for the system dynamics model. Sometimes it never takes off at all. Other times it takes off, but it goes far less high in terms of number of infectives, far less low in terms of susceptibles, and you get a return here. So the one that was closest was which one? Which of these was closest? Random. It was actually quite similar, but you still had die out in some cases. You still had some possibility of die out, but overall it had the closest match to system dynamics because there's no wavefront to speak of. People could reach each other from across the network, but there was still that chance because of quantization that the infection would go extinct. You could see how close, though, the curves are here. They're actually very, very close together in many, many cases. Okay, so ladies and gentlemen, solutions to equilibria for a system dynamics model. Some algebra involved, very powerful, can tell you for all different values of beta and c and tau and the rate of waning immunity, omega, it could tell you, okay, where's the location of the equilibrium? How many people were to be susceptible, infected, and recovered in a very stylized characterization of the world, a very sort of rough characterization of the world where we abstract away from location, we abstract away from details of networks and locality, and we capture things without paying attention to stochastics. But stochastics can be important. It can mean the difference between an infection staying and going extinct. Quantization is also important. It can be the difference between infection staying and going extinct. So here we have effects captured in ABM that are important for practical issues having to do with survival of an infection, its disappearance, the probabilities of certain outcomes. And soon enough, we'll be looking at a way to run these models instead of running it one by one in a manual way, doing sensitivity analyses and parameter variation experiments where we run it hundreds of times and get a summary across all of them about the number of people getting infected cumulatively by the end of the model, et cetera. So we don't have to just run it by hand each time. Okay, so some differences between networks, differences, ladies and gentlemen, between ABMs and aggregate level system dynamics, and particularly paying attention here to the influences of locality, networks, stochastics, and quantization, which are all features notably of ABM. Okay? Okay. Any questions about that? Any questions about that? Okay. So we're going to turn a new leaf, ladies and gentlemen. I'd like you to close all your models. And we're going to take a look at a new chapter within our work incorporating spatial structure within the models, okay? So what I'm going to do is actually switch over to a new video here, and we will